Hello. Remember this? Menke, right? He will write this. He will also write it in index notation. Then you get lots of sums. I don't think I want to go over this again. But if you ever see, I think we did several weeks ago, every matrix, every array has as many indices as its rank. So these have 2 indices. Every time you see a dot in between, you change the adjacent index to the same one. So if it's Gij times CKL, the dot makes it CIJJK. And if you see a repeated index, you sum. That's basically matrix multiplication, and in MATLAB, that's basically the star. That's why I don't think I need to belabor it here. But you will see it in older textbooks, especially when people actually had to calculate numbers using sums and they didn't have matrix laboratory like MATLAB and other packages or libraries. And so you'll see those things written out. So to me, this is all there is to know about the overdetermined inverse. And I think it is high time that we talk about when this is not good enough, when this is not possible, when this is not sufficient. In other words, when this gives you trouble and you need to address it. So let me go to a little problem, maybe. Let's do this here. A little problem, how about that? Here's some data. X, Y. I'll have a linear model. I'll just write it in the usual way, right? Forget the colors. A is the data. M is the unknown. G is the model, including where it has been measured. The experiment contains the x's and the dependency of the x's on the model parameters in giving us D. Think about a alpha equals 1 situation from last time, a polynomial of degree 1, where I will have unknowns, A and B, a slope and an intercept, and that gives me my data, and I want to find A and B, right? And so we know how to do this. In the overdetermined case, when the number of data, which is the row dimension of G, which is called n, is larger than the column dimension of m, which we call column dimension of G, which is a row dimension of m, little m, which we call big M. And our solution, m hat 1, was the overdetermined solution, which relied on the fact that n was greater than m, the traditional dots, 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 and then you fit the line through it. And here right away, I want to go to the situation where my data are just 1 point. And that is clearly a ridiculous thing to ask, you say, because Tuesday I made the point that through n points goes exactly one unique, perfect, zero prediction error polynomial of degree n minus 1. That's the Lagrange theorem, which you know about the invertibility and the squareness of the van der Monde matrix. By the way, van der Monde is a MATLAB command, so you could look at that. And I made the dumb point that if you have 2 data points, that you all know that exactly one line connects it in flat Earth, Riemannian Euclidean space. And so now I'm just taking this down on the data side. Remember the connection here last time, I went and I increased the model parameter space, and I gave you a philosophy about how to select the order of a polynomial, because you would just keep adding parameters, and how do you decide when it's enough? Here, I'm bringing down the help of data, and I'm saying, well, you no longer have an n that is many more than an m. I only have 1 data point. So your inverse problem matrix, the G matrix, is given by 1 and x1, and your data matrix is given by D1. So you all know that this is the solution to this inverse problem, as is this and that and that and any of the bundle that I try to draw that goes through this point, because they're all solutions. So immediately you know that you can't do your usual trick, because m hat 1, our canonical solution, let's say we're trying it and I want you to try it and then fail, is going to be given by, this is the only one I tell you I remember, right, is G transpose times G inverse times dot times, in other words, G transpose GT G inverse GT D times the data, which is a single data point. You all should remember how to multiply matrices. This one here is going to give you a term that is, I'll say 1 over, as in the inverse of a thing that is going to be 1, x1, x1 again, and x1 squared. And I am not hopefully stretching your knowledge of linear algebra much if I'm saying that rather than actually doing it or even attempting to do it, I'll just say that the result of this operation, now I'm using the wiggle for is proportional to rather than the is distributed as that I've used it before as, and then never mind, I'm just going to write it because, you know, it'll end up there, but d1 again and x1 d1 if I ever so tried, but I don't want to look at that because I'm looking at the first term already, and I have reached the point where I'm not finishing drawing my matrix, but rather I want to call on the next person on my call list. How do I make an argument steeped in reality and truth that finishes this equation here? The inverse of this thing, which you see coming as sort of 1 over this arrangement, because I'm just multiplying it out, but I'm trying to skip a line here and come up with the conclusion that said this is proportional to what? Did you take linear algebra? Name 3 things you learned in linear algebra other than it involves algebra and it's linear. Like things, like really, just bring them out of your head. Just throw them at me.
A matrix has to be squared to be invertible.
Okay.
If you have the trace of a matrix is the sum of its diagonal components. If you have linearly independent rows, that is also helpful for a matrix being invertible.
Okay, okay, I like these things. I'm going to go with the second one and I say the trace. Okay, the trace is the sum of the diagonal element. It is also what? What other things that do you know about a matrix that characterizes it, that contains information about it, other than its entries? And the trace is one of them.
There's also the determinant.
Ah, that's the one I want. Okay, so that's the fourth thing you learned in linear algebra, that matrices have determinants, they have eigenvectors, they have eigenvalues, they have traces, they have invariants. And I want to make sure that when I write that the inverse of this matrix is proportional to its determinant, does that make sense to you?
I don't understand why.
Do you know how to invert matrices?
Yes-ish.
Okay, like roughly how do you do it?
You just figure out like what you would multiply it by to get the identity matrix.
Yeah, I like that. I'm going to write it here, you know, A, B, C, D times E, F, G, H must be 1, 1, 1, and please solve that, right? Given A, B, C, D, find these such that the identity results. That's the definition of the inverse. If you do that painstakingly and you organize it, then there are multiple ways of organizing that. But one of them brings out the fact that you need the inverse of the determinant. So if you didn't remember, I'll just say it. That's what you need. What is the determinant of this matrix? So now I'm moving to an actual linear algebra question, which is for the next person. What is the determinant of 1x1, x1, x squared?
Well, with like a 2 by 2, it's 1 over AD minus BC as a...
Right, so I'm just writing what I think you're saying. I do it like this. I think about go down this way and then subtract that way, right? And so the point is determined is 0, and 1 over 0 is infinity, and this thing blows up in your face because 1 over 0 can't do it. So if you know of a matrix that it has a 0 eigenvalue, any 0 eigenvalues, a 0 determinant, therefore, and you need to invert it, you can't do it because it may be square, but it's uninvertible. And this is the simplest case by which you see that immediately. This is a completely underdetermined problem. So the overdetermined and1 solution doesn't work because you would try it and it would blow up. Okay. So, and too small. Other names that now need to come to, they come to my mind, they should be in your mind somewhere. And I really encourage you to dig through your mind and say, what was that all about again? Right? 0 eigenvalues, yes. What does that really mean again? What's it determined again? What is a singular matrix? What is, maybe the other word here that you may have not heard is this problem is ill-posed. The matrix, in other words, is ill-conditioned. Do you guys remember the condition number of a matrix? Is that something you learned in linear algebra? So I think you all should do a little review of linear algebra. I was thinking, if I say, I'll tell you what I learned in linear algebra roughly 7 years ago when I was a freshman in college. Yes, eigenvalues, eigenvectors, determinants, singular values, rotations, the rank, the null space, the kernel, the linear independence of rows and columns, how to multiply them, the ratio of the smallest to the largest eigenvalue, the condition number, which it is, measures of size, like the norm of a matrix. One measure of size of a matrix is what its largest absolute eigenvalue is. Invariants, products and sums of eigenvalues. Obviously transposes, conjugate transposes, symmetries, spaces set up by matrices, how to raise a matrix to an exponential, how to invert a matrix. And then I learned a bunch of stuff that I gladly forgot, like what is a cofactor? What is Gaussian elimination? What is a Jacobian pivoting array? Those are numerical techniques that we used to have to learn because we were supposed to do these things by hand after walking to school through snow on our bare knees for 7 miles. I don't think you should bother with these things anymore, but you should know condition numbers and eigenvalues and singular values and how to transpose and rotate, because all of those things are right here. They're under the hood, evidenced by try inverting this. It won't work, but you see it coming because it's determined to 0. So how about we try to make a quick fix? We'll say, well, we had a problem. Our M1 solution didn't work. So let's try this. Let's try fixing it. So I'm just going to write. I'm really just going to write something that is made up for the same example. Problem is find A and B such that this product is D by 1 and only observable. By the way, I'm giving you a alpha equals 1, find a regression line thing, right? So this bundle, they're all solutions. All of them would have 0 prediction error, right? This is another example of if you're saying, but I found the least squares regression line, I would laugh and say, yes, your sum of squared errors may be 0, and that may be the least you can do, the smallest you can find, because clearly if you put your regression line out here, it's definitely not the solution. This is no good, and this is similarly bad. And then you're saying, oh, I got you a good solution because I have one with 0 prediction error. And then I'm saying, yes, but it doesn't at all help me. First of all, I know that this problem is ill-conditioned for the reason I just said, but also I know that you can find many such solutions, and it becomes worthless to find the best solution if it is one of an infinite number of best solutions, right? Since the space of solution here is infinite, I don't care about your result. So that was an alpha equals 1 polynomial model, which I'm just re-illustrating here, the same problem. I often give the example. Let's go back and say, remember the sort of alpha notation, right, from last time. I just want to restate that problem with that in mind here. Let's say the alpha is 0 statement of this problem is you go to the store, you buy an apple and a pear, you pay $1, and you ask yourself, how much did the apple cost? And if you carry that a little bit further, then you say, well, I don't know. And here's the space of solutions. This is the first time that I make a connection with a space of solutions, and I just give you an even simpler example for it, which is my marginal note here for you to think about. Okay. What is the space of solutions of the price of an apple and the price of a pear, it turns out, if you know that you paid $1 for the transaction of buying one of each? Tell me something about that space of solutions.
It's a straight line from A equals to 1, B equals to 0 to B equals to 1, A equals to 0.
Right. Does everyone see that? Whatever it is, the sum has to be constant and the sum has to be 1 because that's how much you paid, which means that any solution that lies on that line is a solution, and that's by definition an infinitely dimensional space of solutions. And that is yet another way of seeing why that is an underdetermined, ill-posed, ill-conditioned, singular, undoable problem using the usual tools. So now I'm going to do something that I think is reasonable. And I'll say, fine, you can't do this, but you can certainly introduce extra information or extra constraints. And here I'm just going to introduce a few words, extra information, loosely spoken. You'll start hearing the word regularization. We haven't returned to statistics yet again, but you will hear the words a priori information as a way of doing extra information, as a way of regularizing. I'm going to give you an example of a bit of additional information, which is damping or dampening. These are not all synonyms, but these are all words that come up in this context. And I'm just saying, look, you can't do this problem, but I'm going to augment my problem by inventing fake constraints. And let me just say 1, 0, 0, 1 is my new constraint, for which, of course, I have to invent fake data, because otherwise my dimensions no longer work. And so now I'm saying, look, find me the solution from that infinite space of solutions, which is a line. And in addition to fitting the data, also make sure, as one example, that A is 0 and B is 0, but in the sense that you're saying it is 0 because you're trying to make it 0, so you're just going to get as close as possible to it as you can by asking for a least square solution. And so that is the thing I'm trying to do now. I'm saying, well, now, even though I've changed my problem, I have turned it into an overdetermined system, and so now I'm going to try to solve this using the regular way. Okay, so that's my attempt. And maybe I'll just formalize this a little bit by saying, look, in this particular example, I had a G, I had an M, I had a D, and G was singular. So what am I doing? I'm changing my problem. I augment my problem. And the example I just gave you augmented my problem by inventing fake data, which now I say 0, 0, but of course that could be generally anything you want. Actually, I just want to say a 0 array. And in this example of what I call damping, non-limiting, this is a special case, I'm going to slightly generalize it and say, well, you know what? I actually want to supply an identity matrix. And intuitively, I want to say, well, maybe requesting as much as I possibly, as much as I trust my data, I'm asking for A and B to be 0. Maybe I want to somehow relax that a little bit. So I'm going to build in a free parameter, which I'll call lambda, where I'm saying, how about let lambda change and make it a give and take and try to solve this problem. So if I now say, okay, solve used by the usual means, think I've had 5 for my least squares estimate. If I write this down, this minus that and square that and work out this thing, you should see, and please do verify, that I'm requesting a least square solution that keeps the data close to the prediction made by the model parameters that I'm trying to find. I'll write it out the way it comes out if you do the intermediate step, because I like it best how it comes out this way. It comes out as a dot product times the unknowns, and I keep multiplying, and I find that I also have required lambda and m dot m as part of the minimization, and lambda squared comes out. So this really shouldn't be a surprise. I want this to be, for you, not a surprise. So I'm going to look through my old notes here and go, where did I use a phi? Well, here, right? Remember when we did this solution, this is on my page 35, and epsilon is my prediction error. That's what I'm trying to minimize. How am I trying to minimize it? I'm trying to minimize the sum of squared, which I argued it was chi-squared distribute, which I'm sure I've called phi, right? The sum of the squared prediction errors, that's the squares that you least, right? So epsilon, that epsilon, let me just recall it phi here. And yes, I could take a square root of that, or I can normalize it to, like, it's all proportional here. In this case, this is my sum of squares. Oh, and then I did for you the how we actually arrived at the solution. Did I not? Oh, here it is. There was phi the very first time, just maybe 2 or 3 lectures back. Right, doing the same thing, and then I find the norm, and then I went into, oh, what other norms can you find? But we're back to the regular old phi, and then we differentiated this. There we are. So the phi has been there all along with respect to the model parameters, and then you get that. You set it to 0, you solve it, and here, oh, all there. This came out. Okay. Now, if you just go through the same thing with what I've written before, and you just make that new problem, and you keep track of what you've added, and you shove it in there, then your new phi has 2 components: the good old component and the additional component, which comes from you changing that problem. And then if I wanted to go through the same, let's do the same thing. So solve by the usual, grad phi, differentiate in M, collect terms, pull these things out, you end up with a second solution for this newly changed problem, which I'm going to call M hat 2, and I'm just going to write it. And if you have any trouble deriving it, it's just a line or two. It's not a waste of time to do it here, but I don't want to do it now, unless you all go, whoa, where is that coming from? I'd rather point to the solution and talk about it. So you're going to get, remember, of course, it has to be the same if lambda is 0. So you know it's going to involve a GTG inverse, and it's going to involve a GTD times the data. And again, it's a linear operator, no change to a linear inverse problem. But if you work out grad m phi equals 0 vector, then you get this solution, and then you find out that you have added the lambda square identity to your matrix. So this is going to get my second box. I'm going to make it my yellow box. That's the second type of solution to what was a completely underdetermined problem, which by the addition of fake information, I turned into an overdetermined problem, which now has a new solution, and that's what I call M2. So that's the quick fix. And I will yellow box it, and then I want you to look at it some more. And what are the things that I want you to look at? First of all, I want you to see that this here, you need to see that's a quadratic, right? Because it involves the same thing twice, dot, dot, okay? So you also need to make the connection that that's a norm, give or take a square root or a normalization. You know, it's a norm. It's a version of a norm. We had a proper definition of a norm as the pth root of the pth power product of this, but it's a squared norm here. And it's a norm of a residual. And the residual is a prediction error, because remember, we're trying to find the argument over all possible m's that minimize that phi. And so that's literally how you read it. All possible m here is this line. You're trying to find the one that minimizes it. And if you did it the old-fashioned way, you couldn't find the one because they're all equally onely. But here you're now saying, now I have a new problem. I'm also going to try and keep the sum of squares of the model parameters as small as possible. And that allows you to pick out the one. And now, of course, there's a lambda that I can tune to it, and I'll be talking about that. But I want you to see that d minus gm is, again, your prediction error. Remember, we have been calling them little epsilons, the residual. So I want you to write that this involves a norm, a residual norm. Most importantly, this is something that is measuring something in the data space. Of all the values that the data can take, and there's these, lingering things in your brain about linear algebra and vector spaces. And so let me just write this as a norm that measures something about the data and how well it's predicted by the model. And then I want you to see that the second term, of course, is also a norm. But of course, it's a norm that is only in the model space. So the old overdetermined problem with a regular ordinary least squares minimized a data norm and found the best model point that did that, because you could. It existed. It was doable. You wrote the solution, you could do it. Here I'm giving you a solution where if you try that, it definitely doesn't work. And there will be situations where you didn't see it coming. You have your G and you just try it and it's like, it's really actually not working. I'm going to talk about this in 1 second. And then you're saying, well, I need to do something. What do? You add information, you invent fake data, you regularize a problem, you dampen the solution, you supply a priori information, and what you're really doing is you're having a new misfit criterion that combines aspects of data misfit, residual norm, and model misfit, or model norm, model size, measure of something in the model space. And the measure I've chosen right here in this model space is also quadratic, which means easy and doable. And I just stuck in the free parameter because I will talk about it later, and why not? And then I want you to see, of course, that the solution looks exactly like the one before, except I've added the lambda square identity in this case. And then I want you to see that if I just had GTG inverse and I broke it by saying, well, there is a zero eigenvalue with zero determinant, and so 1 over 0, it can't be done because that leads to infinity, then I want you to see that sometimes this lack of invertibility may not be that in your face, but it will just sort of be, well, numerically impossible to invert a matrix. And if you literally try this in MATLAB to give it something that is numerically uninvertible, it's going to actually say, warning, matrix singular, condition number not good, results may be inaccurate, or something like this. And then the numerical way of saying, I need to do something about that. Well, what better thing to stick to a matrix that had whatever it had that led to ill conditioning or singularity or uninvertibility on balance. So now I'm drawing GTG. Ultimately, I need you to see that, one example could be that you have all nice values, A, B, C, and then you might have either actual zeros, this would be another example, or really small values. And this inverse is going to blow up because you will see that if you're doing some linear algebra and if you're doing some tries. And the numerical way of stabilizing this is by saying, oh, I don't know, how about we add little lambdas to the diagonal, because at least that makes this 0 not 0. And so there is a numerical reason, purely numerically speaking, which I really don't actually want to do, but purely numerically speaking, lambda is just a stabilizer, a regularizer, a conditioner, all words, by which you guarantee that you don't have zeros and you're not ultimately trying to divide by 1 over 0. So 1 over something very small. Water level, people call it. You will read the same techniques in 10 different disciplines and they call it all something different. So the addition of small amounts of diagonal elements to an otherwise nearly uninvertible because singular matrix will stabilize it. But you are not asking the question, but the question is on your mind, well, what should lambda be? And like, that's why I want to avoid the purely numerical decision, because clearly, lambda in this case is a weight of a norm in model space. And how does that even compare to the norm in the data space? And even though this is textbook material, I want this to be weird and confusing to you, because you should have no idea how to compare a data norm with a model norm. They're not even in the same units. And how do you weight this lambda? Now that lambda should have units, it's clear that this procedure works. It's clear why it works, but it is also clear that there are unanswered questions about it. Okay, so that is the second type of solution, and that many people discuss it separately as the damped inverse. And so what are the questions raised? What is lambda? How much should it be? And why? It really shouldn't have to be the identity matrix. Why only that diagonal? Why couldn't I add other types of a priori information? If I go back to my apple and my pear, maybe I should say the difference in cost between apples and pears should be small. And then I might have a 1 minus 1 here. And what would I get in that case? So anything goes at this point. We're just inventing ways to turn problems from actually underdetermined to made up overdetermined, and carrying out the implications of that, and then sort of discussing it from a numerical angle, from a linear algebra angle, from a space angle. The statistical angle is about to make its comeback here. And I'm just raising all the questions that should come up your mind. Why this lambda, what the value should be, why an identity could it be something else? And also what that last 0 is, maybe if I call it a priori information, I could try to reconcile, just like, and now I go back to 4 lectures back, the example of the Earth's density. I could make my problem 1 apple plus 1 pear equals $1, and 1 apple costs 60 cents, right? That's a priori information. And now you can go invent a problem where you have 1,000 shoppers that are all reporting their noisy data of how much their apples cost. And then you could supply the prior information that an apple costs about, 60 cents. And then you could incorporate that as a constraint. So what I'm saying here is I stuck in the right-hand side as 0, but maybe this is really just more sophisticated, so-called a priori information. And what form or nature should that take? Clearly, this is going to be the subject of science and statistics, because maybe you have some prior ideas of what it should be. And the other thing that I really want raised in your head already now is, with all of this, I hope to have raised one more concept in your brains. If I say, we're going to do some linear inverse problems, I want to bring in the statistics. And the numerical stabilization, regularization, which takes the form of extra constraints, which gives you stabilizer, which really changes the norm of what you're trying to minimize. And I want to tie all these pieces together, and I want to bring in, like, if I literally say to myself, that's a form of a priori information, like apples need to cost almost nothing, or apples and pears need to cost the same, or the dependence needs to be this. What comes to your mind from our own lectures here that has some bearing, anything at all, about the notion of prior information?
I'm thinking of like Bayes' theorem and kind of building conclusions from data.
Yeah, okay, yeah. Great. That is the word I wanted to hear. Okay, so I'm planting the seed here. This needs to bring up Bayes' theorem, because while I realize I haven't done it explicitly, I'm about to do it explicitly. I go back to page 5, Bayes' rule. And I think even at the time I sort of pointed and said I'd be coming back to it and say, look, think about P, the probability of a model given the data. Think about that being the product of the probability of the data given a model. And that's going to be proportional to some normalization, but also to a prior notion of the probability of model parameters existing or having certain values in the first place. I don't think I did it then. Maybe I did. But now I'll do it. I'll start bringing this back to saying, let A be the model. Let B be the data. Then let's think about the statement of the theorem, and let's call this the posterior. And please, oh please, learn the word posterior. I have seen famous academics misuse this word and misspell it. Posterior, posterior. And this here, I'm trying to make you start thinking about as a prior, a probability density distribution that tells me something about my model parameters before I've even started taking any data. The Earth is flat. All right. My weight is positive. The temperature is autumnal. And then you have this here, the PBA, and that's the probability of having the data given the model parameters that you may be trying. And I'm going to start calling this the likelihood. That's just a word. It is now a word. And I'm going to sort of ignore this now and say, whatever normalizes it for the moment. So just want to have you go back to all of this material and think about, he said prior information. If we're going to make that hard, if we're going to make that quantitative, if we're going to make that statistically sound, it's going to bring back the notion of Bayes' theorem, because it's going to involve knowing something before you even start collecting the data, even if your prior is, I know nothing, it's a uniform distribution, or something like that, something uninformative. It's going to come back. Okay, more things. We are on a roll today. So you guys had the overdetermined solution, and we had some interesting examples, an example where it broke down, a quick fix. I want to give it a third little twist here that naturally arises in my brain, a useful twist, on both M1 and M2. And that is going to be coming out of here, right? So I want to look at this and go, right. Let me not start from a problem, but start now from the minimizer. So now I'm asking my question, what if I went back to the usual overdetermined problem, but I know I've been fiddling with phi for one specific reason. I'd like to fiddle with it a little more. And what if I change phi a little bit? So I'm just going to go back with pretend you have a problem, and pretend you have a phi, and pretend that phi is going to be a quadratic, but just do yourself a favor and say, well, what is the proper definition of a quadratic? Well, it's a product of something with itself, surely. Here's my D. Here's my model specification G, my sensitivity matrix, my design matrix, my experimental matrix, however you call it, however they call it, because they call it all sorts of things, times the model parameters that you pretend are at play, in play, but whose values you don't know. And previously we were saying, well, M1 is going to be the one that just minimizes over the space of all possible M's. Then we said, oops, it breaks down. Then we can change it. And we add a parameter, a constraint on the parameters themselves. Now I'm going back to here and I'm saying, well, if you're willing to take a quadratic, you must be willing to take a more generalized form of a quadratic. And that is something that doesn't just multiply these things together, but rather weights them. Okay. So I'm going to stick in a hypothetical weight. And I make the weight a quadratic itself. And then I want you to just carry this multiplication out, having done some linear algebra, right? So I keep a transpose in here. So I want to move it to the left. I want to move it to the left of D, so that becomes W dot D. Maybe I'll just write it. I'm just doing a few multiplications here in order to actually, I'm mixing notation, which is a little bit dicey, but you'll see it and you'll verify it. I know that the left thing times the right thing is really like, if I wrote it as a matrix part, that would involve the transpose. Here I build in the transpose of this matrix, knowing that's going to come out of the transpose. So now I lose the transpose and I move it to the left. And so I'm going to write it like this times the same thing. So I wrote the interior weight on this quadratic as something that rather explicitly multiplies my original problem. And now I have an unweighted quadratic on a new thing. I'm just too lazy to write it. And so I'll just call this modified problem D wiggle minus G wiggle. And then I'll get a new solution, which I better call N wiggle. And that's my new thing that I want to minimize. And I do it to write it in a form that, of course, I recognize right away. But if I make my G wiggle W times G and my D wiggle W times D, and I hark back to my usual solution of G transpose G inverse G transpose D, but with the wiggles on it, then I'm going to get my third type of solution, which I'll just call N3. With the half for, it's an estimate. And if I rewrite out what I have, then again, I see my GT, G inverse, times my GT, times my data. That was underlying it all as ever. And I find my W's back. So I call that hello again. And that's some sort of a general weighted thing, which is the solution to asking of a linear problem to minimize a sum squared thing of residuals, but something where you attach weight to those residuals, either because you care more about some or others, or you trust the others more than the ones, or whatever reasons you may have. So it's my general form of saying let there be a weight. Okay. So just like the lambda from before, you should now say, well, what the hell is this W, right? How do I even pick that? And now I'm going to make a quick connection that says, all right, fine, this is some general matrix, which I've written as a square, by which I imply it's a positive definite matrix, something that doesn't have negative eigenvalues, by the way. And I'll just say, well, it's some general A. And then I'm saying, well, what should A be? And now I'm trying to bring all of this back to a somewhat grand finale, because I made a point earlier that if we did our M1 solution to the linear inverse problem, and we treated the data as given by signal and the noise, I told you in so many words, and I'm finding my notes on where I did tell you, that you all know that you want your residuals to be zero mean. You all know that you want them to be uninformative. You don't want no more correlations or additional structure. If you do, you got to change your model. And I said, even if you know nothing else about this solution, but you know that there is an objective truth to the model parameters that you want to find, then I told you, and where is it, that the solution was an unbiased form of the truth. Here it was, in my page 31, right? I said, hello, M1, this is it. That's a generalized inverse. That's a linear operator. We know covariance. That was last lecture. Right here, I said, if there is a notion that the data are given by some sort of a true model and a true model relationship contaminated by noise, that if you did this experiment 100 times and collected 100 times of noisy data, and you always went for this sort of a solution, that the expectation of what you would find as the solution from the noisy data would be equal to the model parameters in their true form. That was on this one page, which started by saying the minimal assumption that I have to make is that there is noise, that is zero mean, and that the noise is uncorrelated with the signal. And the signal is given by the true model parameters, linearly mapped by some G that doesn't change. There's no statistical information in G, it's just your experiment. There's no noise in it. So the model parameters themselves are coming from a true distribution. And there is no relation between the statistics of the model parameters and the noise of the data. It's just literally data noise, uncorrelated with what you were trying to find. It's just the jitter in your thermometer or the poor markings on your measurement tape. So you do that, I told you something about the bias. And so this guy, M1 solution, leads to an unbiased solution for a model parameter under a linear model, which is contaminated by noise, which otherwise has nothing to do with the model parameters you try to find. Forget the distribution. We haven't talked about Gaussianity or anything. This is just true. Then we said, well, look, I also know something that came later about the actual covariance of the model parameters, which is one way along the way of you saying something reasonable about how well you do, how much knowledge you have gained. And I went in that tangent of check the residuals, that was point 1, and calculate your model covariance matrix, which was this one, right? So if you have M1, you know something about the expectation of your solution, and you know something about the expectation of the solution with respect to its expectation in the squared form. That's the definition of variance. So you have to put this together, that on page whatever 31, the unbiasedness of the model parameters under this M1 estimate is one point of it. This thing, the covariance matrix of the model parameters, I better do it like this, is going to be, just by the definition, the expectation of M compared to its expectation as a product. Okay, I'm just writing the definition of what covariance means. And I suppose I have written this as, I want to transpose here, right? If my data are column vector, then I want to write it as an expectation of a model vector, which I also treat as a column vector. And then I want to make this object here be a matrix. So let this sink in for a moment. I'm letting it sink in to make sure that I've not made a mistake in writing it at any point earlier, including at the very first time that we discussed writing a weighted mean of something, like the general weight of A, and then, oh no, it is a column vector. It was right. So I want this to be a column times a row. Column vector times the row vector gives me a full matrix, an outer product I'm writing. And I had right on the earlier pages too. I just checked. Okay. So you got a linear problem, you have a solution, you know something about bias, you know something about the variance. I told you that I hadn't proven to you that there was anything good about this variance, that it was special or minimum in any sense. I don't know about the distribution, but I just know it exists and I know how to calculate it. So right now, I'm going to make the final argument here. That is the following. If you choose A, the weight, to be the inverse of the data covariance matrix, then you can prove that, which I say is the model covariance, which I've given you tools to calculate, which you know is a quadratic transform of your data covariance. Now I'm going to call all of that my generalized inverse. I just need new symbols. I just need to pull it all together of the third variety. Previously, I didn't have a W, I didn't have an A, I didn't have this, so it's the same thing, but it just applies right here. And you know how to transform covariances. That's just this error propagation. So here is your negative G, and here's your negative G transpose. That's just notation, right? Don't be confused by that. By 3, I mean it's got a W in it, and by the negative G, I mean that's my notation for the generalized inverse, which previously I have written as G1 negative G. And that connected to Penrose, who got that Nobel Prize, remember? So that thing, which is always true, this is always the case. The if then applies to, and that thing which is just that, as always, is actually minimized. So I'll return to that to hammer this even more home than usual, but it puts together the facts that we're making a linear operator to give us a linear regression. We could clearly define a norm that includes weights. Well, I couldn't tell you anything about what the variance was like before, other than here's how you calculate it. I didn't know what it was with relation to other things. I could tell you about the bias, that it was 0. I could tell you what the variance was in terms of what it was, but I couldn't tell you anything about its values or how low or high it was. But here I tell you that if you stick in the inverse covariance matrix of the data as a weight to build this next linear operator that gives you a new model, that not only is the expectation of the model parameter vector equal to the truth, which is great, but also the variance of the model parameters is as small as you can make it. And the proof of that involves saying, well, what if it was a different matrix and you added something to it and then you work through that and it's like, oh, no, you know, whatever that is, that's the smallest you can make it. I can make this argument later, it takes a little while. So now then I want you to go back and think, aha, 0 bias, minimum variance estimate to a linear inverse problem is going to have a minimum mean square error. Yes, that's right. This is all checking out. This is exactly what you want. You want that efficient, unbiased, minimum variance, consistent estimator. And so that's when everything fits together. This is how it fits together. One last comment before I return to it next time is that this should make sense, right? If you take one data point on a drunk day, or I should say a hungover day, where your measurements are going to be all over the place, there's going to be a big sigma on that data point, a big standard deviation. And you stick this in an inverse problem with a very meticulous, really sharp measurement that you're taking, and you have a small sigma on that because you're doing a good job. If you want to shove data taken on different days by different people with different skills, or by different estimates, different measurements with different uncertainties or precisions into some linear problem that finds the best value of whatever it is you want to know, it should make sense that you want to weight the data by the inverse of the precision, right? A highly precise data point should be weighted heavily in your inversion compared to a low. Well, so that's the best you can do. It turns out that what better thing to stick in than the inverse of the data covariance matrix. And I'll write it out for cases where this covariance matrix is simple like a sigma times an identity, and then you'll see right away what it implies. But it just means decorrelate your measurements and equalize them inversely proportionally to their variance in giving weight to your data in giving constraints to your model parameters. If and when you do that, under the minimal assumption that the model is existing, then your linear solution to your linear problem will give you an unbiased version of the model parameter truth and a minimum variance of that. And then you're done, because then you've solved your problem as best you could.